Hello guys, welcome to week 3. So last week we saw how to do inference on batch mode. So we had three models. One is a rule based sentiment classifier which will run on CPU. Other being an image classifier which was based on ONNX. So I've already briefed on what is ONNX. So if you're not aware about it, I would suggest you go back to week 2 and have a look at what is ONNX format. So it is one other format like we have PyTorch for interoperability purpose, and we would be using ONNX model for ResNet for classification, and then we had a generative model which is Tiny Llama. So the way we were inferring is we were sending the data in a batched fashion, so there was no concurrency. So if I am to explain that illustratively, so let's say that we have three models, M1, M2 and M3, right? So we were first looking at deployment of all these models onto Triton Server with different formats, right? So the idea of last week's demo was how three different models having three different backends could coexist in Triton and do the inference in sequential way, right? So first, right, we would be using only one model at a time, right? It is not going to be a parallel setup. We would first do inference in model 1, get back the results, and then we'll do the inference on M2 and then the inference on M3. You see that it's sequential in nature. So we will not be doing any parallel inference. The objective of today's demos, maybe I'll explain this again illustratively. Same setup, there's no difference in the setup at all. We will have M1, M2 and M3. M1, M2 and M3. M1 being, let's say, sentiment analysis, which is rule based, and then we have image classification, which is ONNX based image classification model based on ResNet architecture, and then we have Tiny Llama, which is an SLM, which is generative in nature. So this is classification, this is rule based, and this is generative model. All three existing in the same Triton server, but they have different backends. Now what we are trying to demonstrate here is how can we do batch inference. When I say batch inference, all of this will happen parallelly. So let's say that you have a batch of 4, right? I'm just making it up, right? You have a batch of 4 batches, and you have batch of maybe like 12, and then you have a batch of 16, right, for the third model. What we could do is we could send all these batches together, right? All these batches in parallel, right? In parallel again to Triton server. I'm putting that as TS Triton server, and what would happen is we will interleave between these requests, right? When the GPU is full, let's say that the Tiny Llama, which is the heaviest of all three, let's say that the kernel is occupying most of the GPU, so the priority will be given to Tiny Llama, and once that is done, right, we wouldn't be doing sequential. We could squeeze any of these models, right? And let's say that there is some capacity of the GPU left for a rule based model. In this case we are anyways deploying this in CPU, but let's say that there is one other model which is lightweight, the kernel of that is lightweight, and we do have capacity. We'll try to squeeze that small model here while we are processing the larger model. So that is exactly what we'll be benchmarking today. So unlike last time where we would be sending the batch in sequence, in this particular demonstration we'll be sending these batches in parallel. And secondly, I'll also be demonstrating not just parallelization, how to profile these, So you should have heard about the metric like P50, right? P50, P95 and P99, right? So these are very important concepts, and let's say that someone would ask you in the interview what are these metrics in terms of model performance. In terms of, when I again say model performance, I don't mean accuracy or recall. I'm talking about the latency, right? I'm talking about the serving time, right? The model serving time itself. What is the inference time, right? So we would be benchmarking this model for P50, P95 and P99. So if I say P50, what is the average inference time? I'm just making it up again, right? What is the average inference time or the serving time for 50% of my traffic, right? And if I say P95, what is the average inference time for 95% of my traffic? And if it's P99, what is the average time of 99% of my traffic? So in production, you would see 50%. Okay, so this is what you would be seeing. 50% is generally going to be less than your 95, generally going to be lesser than your 99. Sometimes your 50 could be way lesser than your 95 or 99, right? So all this would boil down to the SLA that you have set, right? We call it service level agreement. You could have an SLA agreement. Let's say that you are an LLM provider such as ChatGPT, OpenAI, or Claude, or Gemini for that matter. You may have an SLA saying that 99% of my traffic, the time taken for first token to appear should be less than maybe 8 seconds or 9 seconds, right? So when people talk in this language of P50, P95 and 99, they generally talk about this service level agreement. Now, having said that, this is the theoretical part. Let me give you a brief walkthrough, not a detailed walkthrough, but a brief walkthrough of the code itself. So the structure of the project pretty much remains the same. Again, right, in terms of model, there's not a lot of change. So it's just, again, right, just like what you saw in the last week, the model repository has 3 models: image classifier, and the Triton server would be expecting a number similar to this. And like I said, right, this is model.onx format, right, the interoperable format that I was talking about last week. And then you have the sentiment classifier, which again, right, is a basically a rule based model, you can see, right? So it just looks at the keyword, and it predicts, or I wouldn't say it predicts, but it basically sets what should be the sentiment of it, and this runs in CPU, right? And we have the tiny llama downloaded, and you can see, right, this is model.py. You can see that I'm downloading it, right, using the transformers library, and I'm using the Triton backend, and this is the configuration. Now you would see one very distinct configuration for both the ResNet model, the ONNX model, and the tiny llama, that being this dynamic batch, right? So what is this dynamic batch? So you have the preferred batch size parameter of 2, 4 and 8 with microseconds of 500. So the best possible scenario that you would be getting is this 8. So it is like preferred, right? So within 500 microseconds, if you can have 8, right? So the prediction would happen for all these 8 together, right? So for example, let's say that you are not able to assemble batch of 8, right, within this 500, then the next possible best batch is going to be 4, if not 2. Now let's say that you have only gotten 2 requests so far, and your 500 microseconds had already elapsed. It is not going to wait for 4 or 8. It is going to fire all the 2 requests to the inference engine. In this case, it is going to be tiny llama running in Triton server. So that's basically how it would work. So this is the most important configuration change that we have made. So I would also give you a glimpse of what we had last time. This is sentiment classification, right? Okay, so let me open the image classification. It's going to be similar for both Tiny Llama and image classifier. You can see again, right? It is having the dynamic input. In this case, it's going to be 4 and 8. Let me show you what we had last time. So for image classification, you can clearly see that we did not have any dynamic, dynamic batching, right? Although it runs in GPU, but there's no dynamic batching involved here. And you can clearly see that I'm calling this out. You have dynamic batching configured. In this case, it's 2000 microseconds, but the concept pretty much remains the same of whatever I explained using Tiny Llama. Now, having said that, I'll also give you a brief walkthrough of the code that we'll be using to benchmark all these three models. Like I said, right, all three models will be interleaved. The kernel, right, although it has capability, the Triton Server backend, although it has capability to run all these models in parallel, but it can only do that when there is a capacity in terms of GPU. I'm running T4 again sorry, not T4. It is an L4 machine that I've rented using, rented through Jarvis Labs, right? Like what I did in last couple of weeks. The arrangement is pretty much same. So this is an L4 machine that I've rented from Jarvis Labs. It has only one single GPU, right? So let me also show you that, right? You can see, right, it's just one CPU that I've had, and I'm also, you can see that I'm constantly monitoring the GPU for its utilization. You can have this plugged again, right? The health of this can be seen in 8000, the utilization in port 8000 under Docker, and you can actually plug this into any dashboard like Grafana or Prometheus if you wanted to monitor the health of the whole pipeline, right? So having said that, let me show you the code where I would be benchmarking, right? So before that, right, let me run the code because it will take around 1.5 minutes to benchmark all this. So you can see that I'm running this concurrency benchmark.py. Let me run it and explain this. Maybe I'll give you a brief walkthrough of this code, right? Not a line by line walkthrough because it will take a lot of time. And nevertheless, I'm making all this code available to you, right, through lab manual, so that you can practice at your leisure time once you've completed going through this whole tutorial. Alright, so if you go to tests, right, here you have this concurrent benchmark.py. So you can actually see the GPU utilization. It is okay, so maybe I'll show you the fields, right? So this is the number of GPUs. So you can see that it is 0, right? Which means that I only have one GPU. And it also shows you the power, right? I think it's 45 watts. So the temperature, the GPU temperature, it's around 58. Hopefully I'm using this to its fullest so that you would see the temperature. And this is the steaming memory, right? The steaming memory percentage. So you can see that there is an instance where I have used it completely. 97% of this GPU is actually occupied. Right, and yeah, that's basically it. And this is memory, this is streaming memory, this is VRAM memory. So at a particular instance I've used it completely, right, 97% to its fullest, right? And this is for encoder decoder based model, and this is for JPG. If this is for encoder and decoder, if it's video based, ours is not, and if it's image based, this is JPEG, but this is not applicable for ONX model, right? These are like clocks. So having said that, this is the metric basically, right? I'm constantly watching the health of the GPU, but this is the interpretation. This is how you interpret the numbers that you're seeing here, right? So okay, so you can see that yeah, so this is for the sentiment analysis itself, right? What is that I'm sending as an input is text, and what is that I'm expecting is bytes, right? That's what you're seeing here, and you could see that I'm running this in async mode, which means that if it is actually busy, I mean I'm using threading to run this, so that I can run this in parallel using Triton, right? And I also have tiny llama, so you can see that I'm converting the input into an array, and I'm sending this, right? I'm also noting what is going to be the generation time put together. Same would go for the ResNet request. This is going to be the input, right? For color 3 channels, 224 224 is going to be the input, and this is of batch 1, right? And I'm using an image, right? So, and I was talking about the P50, the P95 and 99, and this is the calculation, right, that I'm doing. I mean, this is small function that I've written, which will help me calculate that P50, 95 and 99. And here's where the magic actually starts. You can see that I'm sending close to 200 requests and concurrency to be 40, right? So if you are increasing the concurrency, you would definitely see some failures, because your GPU may not be able to allocate all 40 concurrent requests coming your way, because like I said, right, if the kernel is too big for it to calculate, for the GPU to calculate, it will not allow you to complete all the concurrent requests. You would definitely see some failures. Okay, so you can see that like I said, right, this is like interleaved, right? So to start with, I would be picking any of this, right? And you can see I'm sending this requests, right, with timeout being 10. So if it's taking more than 10, probably I'll switch to a different choice, right? It applies for everything, right? And you can see this is the total requests. Total request is 200, and you can see I'm also capturing the failed ones. So the tasks, and I'm getting the tasks from this total requests. So I'm actually capturing the latencies, because I'm also capturing the time for each of these requests, right? So you can see, right, I'm using lat underscore ms, which is what I'm using for capturing the percentiles that you're seeing here. After this, right, after tiny llama, yeah, you can see, right, this is where I'm actually capturing the latencies. Yeah, so one word of caution, you will not be seeing all the requests, right? So let's say that I'm sending 200, right? You would not be seeing all the requests getting tallied for the completed ones. Let me show you. Yeah, so this is what we've achieved, right? So we've sent 200, right? So tiny llama, out of that 200, was able to process 12. ResNet was able to process 72, and sentiment analysis, which is rule based, was able to capture 56, right? This is the average response time for each of those requests, right? It's approximately 14 seconds, right? So there could be extremes here. There could be request which has had very big response time, so hence you would see the response time having a little bump here, but on an average it is like 6 to 7 seconds, right? So having said that, so this is the P50, 95 and 99 SLA that I was talking about. So this means that 50% of my traffic is having a response time of 59.13 milliseconds, right? And 95% of my traffic, I think this is heavily influenced by Tiny Llama, has had traffic which is equal to 16,000 milliseconds, which is 16 seconds if I'm not wrong, and 99% of it, right, has had the response time of 18 seconds. So if you are doing some sort of streaming service which you would be using remote procedure call, right, if you are doing where you don't have to wait for the entire token to get generated, but stream each token as it gets generated, you may not see this big of a metric, right? So, and you can see, right, out of this 200 requests, 60 have failed because the concurrency is 40, right? Let's say that if I'm reducing this, I would see less number of failed requests. So I'm saying out of 200 requests, I'm saying you'll have to process 40 concurrently. So in other words, let me give you a simple analogy, right? So you run a hotel where you are serving customers, and if you're saying I have a front desk which can handle 200 people, only 40 people can actually dine in a single instance. That is what basically it means in a general English analogy, right? Having said that, I would like to conclude the video. So just to give you a recap, so we started from the last setup, right, where we had 3 models, but we were doing sequential inference. So the objective of last week was how to make 3 models of different backends coexist together. But this time around with the same setup, that is, the coexistence is still there of 3 models having 3 different backends, but the inference itself was batched and it was interleaved, and then we also saw how to do concurrent requests in terms of inference, and finally how do we monitor and profile the SLA of P50, 95 and 99. Like I said, right, I will convert this into a lab manual, and you would have the lab manuals link in the description of the video, right? You can access the link and you will be able to download the whole exercise that I've just done. And if you have any doubts, please do leave that as comments. I'll make sure that I respond to you promptly. Thank you for